We spent the last week or more talking about collisions, and we looked at different kinds of collisions. We can categorize collisions in a number of different ways, like one-dimensional versus two-dimensional. We've already done that. T-bone collisions versus funny angle collisions. We've already done that. Today we're going to classify collisions, not explosions. Everything we say today from here on out is going to involve only collisions, not explosions. Today we're going to classify them in terms of kinetic energy. Now, we know that in every kind of collision, momentum will be conserved, or momentum will stay the same. But in an elastic collision, so will kinetic energy be conserved. Kinetic energy will stay the same as well. So in an elastic collision, momentum and kinetic energy are both conserved. Momentum and kinetic energy both stay the same. In an inelastic collision, momentum is still conserved. As long as we have an isolated system, a system in which we have no external forces, then momentum will always be conserved. But kinetic energy in this case won't be conserved. Kinetic energy here will be lost. The final kinetic energy will be less than the initial kinetic energy. Now, if you had to take a guess, where do you think the kinetic energy would go? We know by the law of conservation of energy, the total energy has to remain the same. But if kinetic energy is lost, then it must be transformed into something else. Whenever you have a collision, if you lose kinetic energy, where do you think the energy is transformed into? Sound, heat, maybe a little bit of light, but those would be the two big ones, heat and sound. So we'll say that that's converted to heat would be number one, and sound would be number two. So momentum isn't transformed into anything because momentum stays the same. Kinetic energy isn't always transformed into something else. If it's an elastic collision, kinetic energy stays as kinetic energy. But if it's inelastic, you lose kinetic energy and it's transformed into heat, sound, maybe a little bit of light. All right, I'm going to give you a couple little tricks. In the end, the overriding principle here is calculate the initial kinetic energy, calculate the final. If they're the same, it's elastic. If you've lost kinetic energy, it's inelastic. If you've gained kinetic energy, you made a mistake because you won't gain kinetic energy. But there's little tricks that can sometimes allow us to not do the kinetic energy calculation. For instance, if the objects stick together when they collide, kinetic energy will every time be lost. You will lose kinetic energy. In other words, if they stick together, it will 100% every single time be inelastic. You don't need to do a kinetic energy calculation in this case because it has to be inelastic. If they bounce apart, so they don't stick together when the two objects collide, then it could be elastic or it could be inelastic. We're not sure. It could be either one. It's actually most likely inelastic because most collisions, probably 90% of collisions are inelastic. But we don't know for sure. It could be elastic. It could be inelastic. If you get a question and you're just not sure like how to do this, and you have to guess, and we hope that that doesn't happen. We hope we don't have to guess on anything, right? We hope we know the answer to everything. But if we do have to guess, if you're in doubt and you do have to guess, what should you guess? Inelastic. Because it's probably going to work for you. It's probably going to work for you, I don't know, 80 or 90% of the time. Like, there's a pretty good odds for guessing, actually. If we can avoid guessing and get it right 100% of the time, that's better. But if we have to guess, being right 80% of the time is pretty good odds for guessing. If you got to guess, guess inelastic, but try to get it for sure without guessing. Now, I want to show you two examples here. The first example, we're not going to solve mathematically. I'm just going to have you read it. This is on the example sheet that I gave you earlier in the year. Just going to have you read it, and we're going to determine whether it's inelastic or elastic just by reading it. And then the second example, we're going to actually solve. First one says a 2,000 kilogram truck traveling north at 20 collides with a 1,500 kilogram car traveling south at 12. They entangle. They head off together at 6.28. Is it elastic or inelastic? And we want you to justify it. So tell me, is it elastic or inelastic? Why do you say it's inelastic? Because they stick together. It has to be inelastic. Now, you could calculate the initial kinetic energy, compare it against the final, but if you did that, you would find that you would lose kinetic energy. We know that has to be the case because they stick together. If you did calculate initial and final kinetic energy, you would not pay any attention to the north and south. How come? Why not? Why not? We've spent so much time circling north and south and saying how important it is, and now we're saying, no, you don't need to worry about it? Yeah? Because kinetic energy is a scalar. Good. So the directions are relevant. It's not like you don't need to put direction in here. It's wrong to put direction in here because kinetic energy is a scalar and it doesn't have direction. So don't make something positive. Don't make something negative. Just make it all positive. Drop any sign if you do have to do that calculation. All right, example number 2. We are going to do this one mathematically because they bounce apart. Now, they bounce apart. It could be elastic. It could be inelastic. If you had to guess, what would you guess? Inelastic. It probably is going to be inelastic. But let's do the calculation just to make sure. We're going to calculate EKI by saying 1/2 m1 v1 I squared plus 1/2 m2 v2 I squared. Now, these masses aren't the same. We have a 5 and a 6 kilogram object. But if they were the same, could we cancel them? No, we could not. Why not? It's not conservation of momentum. In conservation of momentum, the mass appeared in every term, including on the other side. Here it doesn't. It only appears on the right-hand side. Can't cancel them. Can't cancel anything out here, ever. Let's calculate the initial kinetic energy. 1/2 of m1, 5.0 times v1i is 0.98. Square that, plus, what's the kinetic energy of object 2 there? Who said 0? Why is it 0? Why is it 0, Austin? Right, it's at rest. Do the math there, works out to be 2.4 joules. So the initial kinetic energy to 2 digits is 2.4 joules. We go to 2 digits, right, because of this, and all my data is two digits there. Now let's calculate the final kinetic energy. We're guessing that it's going to be below 2.4 joules, but we don't know for sure until we actually do it. 1/2 m1 v1f squared plus 1/2 m2 v2f squared. What's v2f? Sorry, v1f. The lighter ball, the 5 kilogram ball, 0.6 at 50 degrees. Or we'll just say 0.6. Why are we not paying any attention to the 50 degrees? Cameron told me a minute ago, right? It's not a vector, it's a scalar. The direction doesn't matter. Like, don't ever do x and y components here. Don't ever get rid of the funny angle here. Right? Like, that's a vector analysis. This is scalar analysis. We don't care about the direction here. Mass, the second one is 6 kilograms, and the speed, not the velocity, because we don't want the direction. The speed here is 0.63 meters per second. Yeah, we don't care about that either. Solve this, it works out to be 2.1 joules. Oh, they're close. Close. Close enough? Nope. Nope. The final kinetic energy is less than the initial. We'll say EKI is greater than EKF. Therefore, it is inelastic. Nice to see a question with all these funny angles in it and then not have to worry about it. Just do it nice and straightforward like this. Yeah? Oh, good question. good question, almost as if I planted that question, because that was the next thing that I was going to talk about, actually. What if we had two unrounded numbers here? They're 2.4 and 2.1, but let's pretend for a second we had 2.401 in the first one, and we had 2.399 in the second one. Would we call that elastic or inelastic?
Elastic.
No. No, we'd call it elastic. Why would we call it elastic?
Because it's significant digits.
Yeah.
These active as digits.
To two digits, this would be 2.4, and to two digits, this would be 2.4. Somebody in the last class said that doesn't make any sense because we've got these other numbers. Like, it's kind of like cheating to say like, but it's not. The whole point of significant figures is to say, look, if it's only two significant figures, the last two digits here, we don't really know to any degree of certainty. Like, what's not right is if you say this is inelastic based on uncertain digits. We're certain about the first two digits, and to those two digits, it would be elastic. We're not going to base our conclusion about what we're not certain about. We're going to base it on what we are certain about. What if it was to three digits? Would we say it was elastic or inelastic? 2.40 and 2.40 to three digits, it would be elastic. And what if we had to record it to four digits? Jacob? This would be inelastic, because to four digits, we've got 2.401 and 2.399. Got it? So, Austin, to go back to your question, what about significant digits? If to the correct number of digits, it rounds to the same number, it's elastic. If it doesn't to the correct number of digits, it's inelastic.